Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 2, Lecture 4, Dynamic Atomic Force Microscopy Methods. The last time in class we had talked about the analytical theory, the analytical basis for dynamic atomic force microscopy under conditions where the tip amplitude cannot be considered infinitesimal with respect to the tip sample gap, which required a very different approach, a mathematical approach to understand the basic physics of image formation and material contrast in all dynamic AFM modes, whether they be tapping mode, AM-AFM or frequency modulated AFM. At the heart of the analytical methods that underpin both approaches are two important quantities, E sub ts and V sub ts. E sub ts is the tip sample energy dissipation in one cycle of oscillation. This is the energy dissipated by the oscillating tip into the sample in one cycle of oscillation. As shown here in the equation 2, the physical interpretation of it is shown on the graph on the bottom left, where you see the area under the hysteretic force versus force against D, tip sample gap curve, gives you the energy dissipated in one cycle of oscillation. The important thing in the last class we also derived was we derived a relationship between ETS, which has this very nice physical significance in terms of tip sample interaction forces, in terms of the observables in dynamic atomic force microscopy, things like the excitation amplitude F0, or the drive frequency omega, or the natural frequency omega naught, or Q, or the spring constant of the cantilever K. So the second equation now is linking observables in dynamic AFM to tip sample interaction dissipative properties, ETS. The second equation we derived was this quantity, which is the average value of the product of the tip sample displacement times the conservative force it encounters during a cycle of oscillation. We pointed out that this quantity is often called the virial because the equations that we derived can also be derived using the application of the virial theorem. But the important thing is the physical significance of the virial was most apparent by taking the integral and going through an integration by parts and writing it out in terms of an integral of dq. And that told us that the real interpretation of this quantity VTS, it can be seen from the graph on the bottom right, which is if we were to graph the gradient of the tip sample interaction force KTS as a function of D, the tip sample gap, and if one looks at how much the range over which the tip oscillates back and forth, if one looks at the area under the KTS versus D graph that's traversed during the tip oscillation, and one weights it by a function as shown in the shaded blue on the graph on the bottom right, the product of those two is what is VTS. And in the limit of very small oscillation amplitudes, VTS is nothing but 1/2 KTS times amplitude squared. So the virial really is a integrated measure of the energy stored in tip sample interaction, conservative energy stored in tip sample interaction forces as the tip oscillates. And ETS is a measure of the dissipative total energy dissipated during one cycle of oscillation. And both, while they have this very nice physical significance, are related to or can be measured or quantified in terms of observables in dynamic AFM through equations 1 and 2. Now, moving forward, what we wish to do today is derive some equations that we can then specialize and move towards amplitude modulated AFM and specialize and move towards frequency modulated AFM. For doing so, we go to equations 1 and 2 and eliminate phase between those two. The details are shown in the appendix. We arrive at a very important equation, equation 3, that tells us how the amplitude A changes when there are tip-sample interaction forces. What one sees in equation 3 is a beautiful, elegant result. Equation 3, if you think about it, has the same form as the amplitude ratio or the magnitude of the transfer function we talked way back in week 1 for a directly excited cantilever, except in the denominator we now have an omega naught prime and a q prime, which are described in equation 5 and 6 as clearly stating that omega naught prime is now the natural frequency of the oscillator, which has been changed due to the virial, the VTS of the interaction, and the Q prime, which is the effective Q factor of the oscillator, that's been changed due to the tip sample dissipation E sub TS. And the important thing here is that unlike what we discussed with the linearized theory, VTS and ETS are actually quantities that depend on A and on Z, both quantities. And so these are sort of nonlinear. VTS and ETS depend in nonlinear fashion on Z, the gap, or the tip sample distance, and the oscillation amplitude A. So we have the modified natural frequency omega naught prime, the modified effective Q factor Q prime due to the ETS terms. Both of them make their way into the denominator of equation 3, telling us that you can think of the resonance response in the following fashion as shown in equation 3, very much similar to what we derived for a directly excited cantilever some time ago. However, what ends up happening now is that omega naught prime also depends on the amplitude, and Q prime also depends on the amplitude. So we have an equation in equation 3, both the left-hand side and the right-hand side contain the amplitude. We'll try to discuss the significance of that in the next slide. In a similar fashion, the tangent of phase is defined exactly in the same way as we defined it in the last week, except now we have this modified natural frequency omega naught prime due to the VTS, the virial term, and we have Q prime due to the ETS that modify our expression for the phase lag. It's important to note that we derived a result last time that when you have infinitesimally small, really small oscillation amplitudes in the linearized limit, the V sub TS can be expressed as 1/2 KTS times amplitude squared. KTS is the tip sample force gradient. When we plug that into equation 5, we get a very classic result. The modified natural frequency actually equals 1 minus KTS divided by 2K. And this is just the linearized result of the frequency shifting due to a change in force gradient, something we derived when we did the linearized analysis. So equations 5 and 6 are very fundamental global equations that in the linearized limit reduce to what we had discussed earlier. But they're in fact valid for much larger amplitudes as well. So now what we do is we take the equations we derived previously and now focus on how we would zoom in and use it to understand the physics of image formation and the material contrast in tapping mode or AM-AFM. Well, first of all, when one tries to work on AM-AFM, one tries to tune the cantilever far from a sample and chooses to have a drive or excitation frequency omega equal omega naught. This is typically the case. Sometimes we may want to have it slightly off omega naught, but for the moment, as far as the theory is concerned, let's focus on the case where omega equals omega naught, and we keep the drive excitation, the excitation magnitude constant. F naught is constant. Now, in these conditions, recall that we had a derived result for directly excited cantilevers far from a sample, or without tip sample interactions, that F naught, which is the magnitude of excitation force, must equal K times amplitude divided by Q. In this case, the amplitude is the amplitude that you choose to oscillate the cantilever at far from the sample. Now that we're interacting with the sample, we must distinguish the amplitude far from a sample from the amplitude encountered while scanning the sample. So we call the amplitude far from the sample as A super far. So the magnitude of the excitation force far from a sample is simply going to be K A far divided by Q when the drive frequency equals omega naught. The phase lag in this case is going to be 90 degrees, or pi over 2. In this case, we can show, as shown in the appendix, that the virial and the energy dissipation expression simplify to equations 7 and 8, and you can eliminate phi between equation 7 and 8 to get the amplitude reduction equation 9, which tells us what is the ratio of amplitude encountered when the oscillating tip starts interacting with the sample. That's the steady state amplitude. And A far is the steady state oscillation amplitude when the tip is withdrawn from the sample. So equation 9 is a classic equation for tapping mode atomic force microscopy. It's called the amplitude reduction equation. And again, this equation is equally valid for small oscillation amplitudes or large oscillation amplitudes. In other words, it's the most uniform or general equation in tapping mode AFM. And equation 10 is the corresponding equation for phase lag, tangent to phase lag. What one notices is this equation 9 contains the amplitude A on the left-hand side, because we have the amplitude reduction on the left-hand side. On the right-hand side, we have VTS and A squared in the denominator. And VTS itself depends in a nonlinear fashion on Z and A. So does ETS. So what we have in equation 9 is a nonlinear equation that tells us how the controller would want or try to change the Z value over the sample in order to keep amplitude constant, in the face of the fact that as one scans point to point of the sample, the ETS and VTS are going to change from point to point of the sample due to changed material properties, for example. The ratio of amplitude, the steady amplitude when you're engaging with the sample and tapping with an amplitude A to the amplitude far from the sample A far, is called the amplitude set point ratio. So when it's 100%, it means you're not interacting with the sample. When the ratio decreases to below 100%, to 70%, 80%, it means as you've come closer to the sample, the oscillation amplitude has changed due to the tip-sample interaction forces which are contained in the ETS and VTS terms. So ETS and VTS, because they appear as squared terms in the denominator of equation 9, as ETS and VTS increase in magnitude, the amplitude starts decreasing as you approach the sample. So the consequences of these equations are the following. When one is scanning the sample in tapping mode, what Z is going to try and adjust itself so that ETS and VTS reach a value where the desired amplitude is maintained. What I mean by that is, as an experimentalist, what one does in tapping mode is one chooses the set point amplitude ratio. As the scanner is scanning over the sample and there are topography variations, the Z is going to change at point to point of the sample, because Z is the gap between the undeflected cantilever and the surface. As the surface topography changes, Z naturally changes. As a result, ETS and VTS are going to change, and with them the amplitude is going to change. So what the controller tries to do is it tries to change the Z even further in a way such that ETS and VTS change their values so that the denominator of equation 9 remains constant, and the constant amplitude is maintained across the sample. Thus, the topography in tapping mode AFM can be regarded as those values of Z which allow the achievement of constant amplitude as one scans the sample, while having possibly point-by-point variations in ETS and VTS. In other words, the topography in tapping mode AFM is influenced by a combination of conservative tip-sample interaction forces contained in VTS and dissipative interaction forces contained in ETS. The other important thing that emerges from this analysis is that ETS and VTS, the dissipation and virial, are not independent quantities in tapping mode AFM. They are actually related through an equation, the amplitude reduction equation, and through the phase relation, which means if I'm doing tapping mode AFM and I know the amplitude reduction, if you tell me what is E sub TS, I can tell you what V sub TS must be through equations 9 and 10. The other important thing, the last important thing that emerges from this is that the phase lag equation depends on both ETS and VTS. We're going to talk about phase lag in the next lecture in some detail, but the key point is that both these properties conspire to influence the final value of the phase lag. Let's now specialize the equations derived at the start of this class towards frequency modulation. In frequency modulation, we do three things. We keep the excitation frequency changes in order to keep the phase fixed at 90 degrees, phase lag at 90 degrees. So we go back to equation 4 at the start of this lecture and set the phase lag to 90 degrees, which requires omega, the excitation frequency, to equal omega naught prime, which is described in terms of VTS as shown here. So which means that the requirement that the phase lag equals 90 degrees requires that the omega excitation frequency is tuned to equal the modified natural frequency omega naught prime. So we have a very nice way of tracking the modified natural frequency by tracking the phase through the phase lock loop. The second thing one does in frequency modulated AFM is changes F naught to keep amplitude fixed. So we go back to the amplitude reduction equation and require that keep omega equal to omega naught prime so that the phase is at 90 degrees, phase lag is 90 degrees, and find out what should be the value of F naught. We find this very nice expression for F naught in terms of ETS, the tip sample interaction, the dissipation between the tip sample due to the tip sample interaction. And this tells us that as one scans over the sample, when F naught changes, or whenever the tip sample dissipation, ETS, changes, F naught must change or increase in order to keep the amplitude constant. So F naught really becomes a measure of the tip sample interaction dissipation, or the energy dissipation between the tip and the sample. Finally, in order to create a topography, what we do in FM-AFM is change the Z value so that the frequency shift, which is omega naught prime minus omega naught, remains constant. From the expressions we derived earlier, this frequency shift is given in terms of the virial VTS divided by Ka squared. In other words, we're changing Z to keep, because omega naught and K are constants, we're really changing Z to keep the ratio of virial divided by A0 constant. So when one scans the sample, we're moving the base of the cantilever up and down in order to maintain a constant frequency shift and then maintain, therefore, a constant value of the virial divided by A squared. This leads us to the following conclusions, that when we deal with frequency modulated AFM, the topography that's rendered is the set of those values of Z that keep the ratio of VTS divided by A squared constant. This is equivalent to saying keeping the frequency shift constant. The drive frequency automatically tracks the effective natural frequency omega naught prime, and F0 or F naught changes to pick up the dissipative interactions between the tip and the sample. So the analytical theory of AFM using the virial and dissipation, which are linked to the observables in dynamic AFM, allows us to interpret the physics of image formation both in tapping mode AFM and in frequency modulated AFM, and also tells us the physics of the contrast channels in both cases. In the case of tapping mode AFM, the contrast channel is formed due to the phase lag image, and in the case of frequency modulated AFM, the contrast channel forms due to F naught, or the excitation amplitude change due to the dissipation. And we'll talk about these different channels in the next few lectures. But for the time being, the basis from which we understand both these modes from an analytical perspective is now covered. Thank you.